Hello there. In this lesson, we're going to learn about formation reactions and another way to find enthalpy values that doesn't necessarily use Hess's law or calorimetry. So, formation reactions, there's three of them written here. What can you see that is common about them? Well, one thing hopefully that stands out is that there's always only 1 mole of product, and only is one product, right? And that everything on the left-hand side here is all elements, right? Oxygen, hydrogen, carbon, hydrogen, oxygen, nitrogen, right? And you also see that there's some fractions here in the balancing, and there's a reason for that as well. So what is a formation reaction? Reaction produces 1 mole of a substance, that's why there's only one product, from elements in their standard state. So first of all, 1 mole of product, that's why all of the right-hand side of those examples before all only had one product and only 1 mole of it. And then standard state, well, elements in their standard state are what are shown on your periodic table in your classroom, or if you have a color one in your binder or textbook. The reds here are all gases, the blues are liquid, and the blacks are all solids. The ones that have the outline we probably won't be using anyways, but they're the ones that are made in, not found in nature, so they're made in chemical or nuclear reactors. So if you want to make the formation reaction for water, so water is the product, and then you got to take elements in their standard state. So we need oxygen and hydrogen, which are both gases. So hydrogen, Hofbrinkel is a gas, and then oxygen, also Hofbrinkel is a gas. Now, if we need to balance this, we got to end up with 1 mole of product. And so that's why you're going to need fractions for balancing. We already have 2 hydrogens, so that's already balanced. It's the oxygen. I have 1 mole of oxygen in my product, and I have 2 in the reactant, so I have to use a fraction here, 1/2, to balance things out so that you still keep the 1 mole of product. So here's a little game, see if we can pick out the proper formation reaction for the formation of lithium carbonate. Right, so we got lithium carbonate, 2 lithium carbonates here, so it can't be that one. That's a big X because you got 2 moles of product instead of 1. Here is okay, and here is okay, so that's good. How about the other side here? We got liquid lithium on the first one. Oh, that doesn't sound right. Lithium's not a liquid in its standard state. Carbon's a solid, oxygen's a gas. Here we are, lithium is a solid. Great, there we go, ding, ding, ding. This is our formation reaction. Yay. So why bother with enthalpies of formation? Well, they can be really useful in finding the enthalpy of reactions if you know all the enthalpies of formation of the compounds in your reaction that you're studying. So it's like a shortcut to find the enthalpy of reaction by using known enthalpies of formation. And you'll notice that on the table here that we don't have any enthalpies for elements in their standard state, because let's say if you're going to write a formation reaction for an element in its standard state and you're going to make it from elements in its standard state, well then there's no change, and so of course it's going to be 0 for the value there. So you won't find any enthalpy values for elements. All the other, I guess you'll find them for non-standard states like this diamond here, which is a little different than just carbon as you would normally find it. But regular standard state elements won't be on the table. So in order to determine the enthalpy of a whole reaction from formation reactions, you can kind of think of it as unforming your reactants and then reforming those same elements into the products. And since you can work out the enthalpies of formation for both, all you need to do is like switch the sign for the enthalpy of formation of the reactants and make it unforming, right, rather than forming those. And it's like you're taking these reactants apart into their component elements and then reforming all those elements back down here into the new products. And so this is going to absorb some energy to take apart the bonds that were there previously. This is going to release energy as new bonds are formed, and the difference will be your overall enthalpy of the reaction. Okay, so you can use Hess's law for this if you like. What you can do is look up the enthalpy of formation for each one of the compounds that isn't an element, and then add them up in order to see if you can get the overall reaction. So we'll start with this benzene, C6H6, which is here, which has a formation enthalpy of 49 kilojoules per mole. So what we want to do is flip that around and make it an unforming. So C6H6 turning into 6 carbons and 3 hydrogen molecules as a gas, right? There you go. And the enthalpy for that will be the opposite. So delta H for that will then be negative 49 kilojoules. Okay. The oxygen is an element at standard state, so we can skip that. We have carbon dioxide here, and we have 6 of them. So 6 carbon dioxide gases. So here they are. Oh, that's, yeah, carbon dioxide as a gas right here. And it's negative 393.5 kilojoules per mole. So we have carbon dioxide. We have 6 of them here. So we want 6 carbon dioxides. So that means we're going to need 6 carbons and 6 oxygen molecules, all gases, all solids. And the delta H for that is going to be 6 times the negative 393.5 kilojoules because we have 6 moles of carbon dioxide that's being made. Great, check, got both of these done. Let's do the water. We have 3 waters being made. This is water as a gas. So I'll go down here, water vapor. There it is. Negative 241.8. So delta H for this is going to be 3 times negative 241.8 kilojoules because we have 3 moles of water being formed, which means we're going to need 3 halves of the oxygen, and we're going to need 3 H2s to use that up. So that's a gas, and this is a gas. And then let's see if this all adds up to our overall reaction. So we got our benzene there. I'll switch colors just to make it a little clearer. We got our benzene, C6H6. And then we have oxygens. So we have 6 oxygens. It's 15 over 2 here. So this is 6 oxygens. That's 12 over 2, 12. And then we get 3 more here, 13, 14, 15. So great, 15 halves oxygen. And then we have 6 CO2s and 3 H2Os. And does everything else cancel out? We get 6 carbons, 6 carbons. We have 3 hydrogens. We got 3 hydrogens. And I think everything else is part of the equation. Great. So delta H for this whole reaction then will be the sum of those. So let's see if I can work that out. So I get negative 3,135.4 kilojoules for that one. Another way to solve for enthalpy changes is to use a formula along with the enthalpy of formation of products and reactants. So just to show you how it works here, if you want to find the overall enthalpy change of any reaction, you're going to take the sum, that's what this symbol is, the sum of the number of moles times the enthalpy of formation of the products from the table. And then you're going to subtract, again, the sum, the number of moles times the enthalpy of formation of the reactants off the table. So you see you're subtracting the reactants. That was the same as when we flipped the reactant when we were doing Hess's law, changed the sign of the enthalpy of the reactants. And so yeah, you can use this formula and it'll save you a little writing out like you have to do with Hess's law. So let's use it with that exact same example we did before and see if we get the same answer. So we want the enthalpy of the overall reaction. and we're going to add up moles times the enthalpy of formation of the products. So these are the products here. So we need 6 moles of carbon dioxide and 3 moles of water. So we'll say 6 times, and the carbon dioxide was this guy, 393.5. 393.5 kilojoules per mole. And this is 6 moles, right? So the moles cancel out. And yeah, and then we're going to add that to 3 moles of the water times the 241.8. So negative, oh, I forgot the negative here too. Negative 241.8 kilojoules per mole. And you see that moles again cancels out. Great, we're doing good so far. And then we're going to subtract the number of moles times the enthalpy of formation of the reactants. So we got 2 reactants here, but this one has an enthalpy value of 0, or enthalpy formation value of 0. So we can ignore it then. So that only leaves us this guy. So we look up benzene. There it is. So we're going to subtract. We got 1 mole of benzene times 49.0 kilojoules per mole. And you see again moles cancel out. And so if we add all this up, we should end up with that same enthalpy value. So 6 times negative 393.5 is negative 2361. And we're going to add that to 3 times negative 241.8. And that comes out to negative 725.4. And then we're going to subtract 49.0. These are all kilojoules. And we'll see what that all adds up to. So add or subtract the 49 and subtract the, I ended up with negative 3135.4 kilojoules, just like the other one. Yay!